The main objectives of this section, in fact, as I said, is to summarize the techniques that you have learned so far. So we will summarize here these techniques as we will list them as guidelines. So to sketch a curve or a graph of a function or equation by hand, it is better to follow the following steps, ya shabab. First, start with the domain, then the intercepts, the x-intercept, the y-intercept, then check the symmetry behavior of the function. Is it even? Is it odd? Is it periodic? Also find the horizontal and vertical asymptotes, and also the oblique, the slant asymptotes. We will focus on that on this issue in this section, the slant asymptotes, how to find them. And of course, the intervals of increasing and decreasing, and local and the local and also absolute if you can, local and absolute maxima and minima. And of course, the concavity and points of inflection. All of these issues, they will help you to sketch the graph of a function. So as I said, you will start with the domain and then the intercepts. Then you will see if the function is even. You need to remember what we mean by even, Shabab. Like these functions, x squared, x to the power 4, and so these are examples about some even functions. The odd, what is the benefit? What is the benefit from knowing that the function is even or odd? It will be, of course, clear for you that the function, if the function is even, then it will be symmetric about the y-axis. So you have an idea. So the graph will be symmetric about the y-axis, like what you have for the x squared. So it will be something like that. And if it is odd, it will be symmetric about the origin. It will be something similar to the x cubed, like this. So it is good. It will give you an idea. You can check your graph. Is it correct or not? And you know that there are functions that they are neither even nor odd. For the periodic also, it is important to know if the function is periodic and what is the period. And remember sine, Shabab, to sketch the graph of sine x, for example, it is enough to sketch the graph between 0 and 2 pi. After that, you will just make a kind of transformation. You will just write it again or draw it again. So it is enough to know it within one period only. So if you can know that your function is periodic, is okay. The horizontal asymptotes, how to find the horizontal asymptotes? You will just find the limit of the function when x goes to infinity, or also when x goes to negative infinity. If you have a number, if this limit is equals to a specific finite number, then this number y equals L is a horizontal asymptote. Even if it is not L, by the way, it is helpful. If you, for example, got that f of x when x goes to infinity is infinity, this is also a helping information. This tells you that when x goes to the far right, the function will go to infinity, to far up. So also this will help you when you sketch the graph. It will you will have an idea about the end behavior of the function. What else? The vertical asymptotes. How to find the vertical asymptotes of a function? To find the vertical asymptotes of a function, you need to find out a number, a value for x at which the function is not continuous or not defined. And then check the limit from the left and from the right. If the limit from the left of that number or from the right is equals to infinity or negative infinity, then x equals a is a vertical asymptote. Usually, when you have rational functions, for example, usually this will happen at the zeros of the denominators. But be careful. Sometimes we have a whole, not a vertical asymptote for some functions. So when you find the vertical asymptote, you should simplify your function like this. You should have x squared minus 4 over x minus 2. What do you think? Do we have here a vertical asymptote at x equals 2, or we have a whole? If you simplify this, you can see clearly that it will be equal to x plus 2, because x minus 2 times x plus 2, so it is x plus 2. So it has no vertical asymptotes here. It has a whole. So this is should be done after simplifying, not before. طبعا here x is not 2. The slant asymptotes. This is the main part of this section, ya shabab. How to find the slant asymptotes or the oblique asymptotes. I have noticed that all the old exam questions are about this, because for sketching the graphs and increasing, decreasing, and blah blah blah, we have done them before in the previous sections. The interval of increasing and decreasing, you know that the function is increasing if the derivative is positive. If the derivative is negative over specific interval, then it is decreasing. What else? The local maximum minimum, you know, you have two tests. You can use the first derivative test or the second. This is up to you, but of course we prefer, shabab, the first because it is easier. The concavity and the point of inflections, just you need to find the second derivative. And of course, by the way, if you have a problem and you already have the second derivative, it is good also to apply the second derivative test, because you already did. Usually we avoid, ya shabab, the second derivative test because we don't want to find the second derivative test. But if you are forced to find the second derivative test, use it. So you can have, you know that if the second derivative is positive, then it will concave up. If the second derivative is negative, it will concave down. And finally, sketch the graph. Let's apply these ideas or these guidelines to this example. I will ask you in the quizzes to do that. If we have a written quiz, I will ask you to sketch the graph. Otherwise, I will ask you about these issues, not about the graph itself. Now use the guidelines to sketch the curve of this function. You can see that this is a rational function. You have polynomial over a polynomial. So this is easy, by the way, not difficult. You can know many things, but let's follow the guidelines. So first of all, we need to find what? The domain. A domain. What is the domain of this function? Just look at the denominator. It is all the real numbers except 1 and negative 1. So just we need to remove 1 and negative 1. The x-intercept and the y-intercept, both x equals to 0. What you will have? 0. So the y-intercept is 0. And the x-intercept, both y equals to 0. Both this equals to 0. If this is equals to 0, means the numerator is 0. The numerator is 0 when x is 0. So for both, the x-intercept and the y-intercepts are 0. So here it means that the x-intercept is x equal to 0 and the y-intercept is y equals to 0. Which means 0 and 0, the origin here, it is the x-intercept and the y-intercept. So now you have an idea. The graph will pass through the origin. This is one thing that we know about it. And of course, we have at negative 1 and 1, we may have a vertical asymptotes. You need to check, can you simplify here? Can you do anything? No. So I think we have at negative 1 and 1, we have a vertical asymptote, 2 vertical asymptotes. What we need to make sure about, just we will find the limit. What will be the limit of the function when x goes to 1 from the left and from the right? And similarly, we will do that for negative 1. If the result is infinity or negative infinity, so we are done. It is a vertical asymptote. Now, what else? The symmetry. What do you think? Is this function even? If we replace x by negative x, it will stay the same. So it is even. This function is even. So what we know about that? What is the benefit of knowing that it is even? It will be symmetric about the y-axis. So if you sketch it here like let's say like this. So here it will be similar to that, like this. Okay. So what else? The asymptotes. We need now to find the vertical, the horizontal asymptotes. We will not focus on the slant until we study them. Now, to find the horizontal, let's start because it is easier, shabab. To find the horizontal is much easier. Just take x, let x goes to infinity, and then to negative infinity. Let's start with positive infinity. So if x goes to infinity, shabab, you have the same degree, so it will be this over this, it will be 2. And of course, the result will be 2, the coefficient here over the coefficient here. And when x goes to negative infinity, because we have here x squared and here x squared, it will be the same. So this is why he combined them together. So what we conclude from this, يا شباب? So what?
2 is a horizontal asymptote.
Y equals 2. Be careful. Y equals 2 is a horizontal asymptote. It is a line. Yes, you're right. So we conclude that the line y equals 2 is a horizontal asymptote. Now to find
Yeah.
Yes.
What becomes like this? 1 minus 1 over x squared.
Sorry?
The limit, how it changed to 1 minus 1 over x squared?
Divide by x squared. You know, yeah, Hashim, when you have a limit when x goes to infinity, what usually we do? We divide by the highest power. Just he divided by x squared.
Okay.
خلاص يا شباب, now even if you have L'Hopital, by the way, if you want, but no need يا شباب. You know يا شباب, when the limit of the function, rational function px, let's say px over qx, you have three possible results. It is either, let me go back here and write it for you. It is either the leading coefficient of p over the leading coefficient of q, or 0 or infinity. These are the three only possible cases for the rational functions when you have a polynomial over a polynomial. This will be if the degree here, this case, if the degree of p equals the degree of q. Here we will have it if the degree of p is less than the degree of q. And here we will have it if the degree of p greater than the degree of q. Is that clear, Shabab? I think this, you should know this from before. So clearly here we have the same degree. So it will be 2 over 1, the leading coefficient here over the leading coefficient here. It is clear. This is only when x goes to infinity or negative infinity. You have to be careful when it is going to negative infinity. If it is odd or even, or that one odd or that one or even, it could be here positive or negative infinity. Now for the vertical asymptotes, just look at, because it is rational, go and look at the zeros of the denominator. Now find the limits when x goes to 1 from the left and from the right. What do you have? If x goes to 1 from the right, so it is greater than 1. So this one, Shabab, it is x minus 1, x plus 1, the denominator. When x is greater than 1, this will be positive. And this is already positive. So positive or positive, it will be positive 2 over positive 0. So it will be positive infinity. Here, when x, it is x minus 1, x plus 1. When x goes to 1 from the left, this will be negative. So it will be positive 2 over negative 0. So it will be negative infinity. Similarly, for negative 1. If you check negative 1 from the left and from the right, why you need to know this, Shabab? You need to know. Some of you, they said, Khalas, I know it is vertical asymptote. So why should I do this? Because you need to sketch the graph. So this is 1. This is negative 1. So you need to know, is the graph here doing like this or doing like this? Is it going to infinity or to negative, or it is doing like this or doing like this? You need to know this. So you have to check, is it going to infinity or negative infinity, to the right and to the left? So you must do this to sketch the graph. Now let's summarize, by the way. Initially now we have some ideas. It is important, yeah, Shabab, after this step, after step number D, check like what we can call it a preliminary sketch or initial sketch. So now what can we do? I have that the x-intercept is 0 and also the y-intercept. I have a vertical asymptote at 1, a vertical asymptote at negative 1. Also we have a horizontal, what is it? 2. We have a horizontal asymptote which is 2. Now I can imagine now how my graph will look like. Can you help me with that? Now when x goes to 1 from the right, 1 from the right, it is going to where? To infinity. So it will go this way. The graph will do this. And when it is from the left of 1, it goes to negative infinity. This is the left of 1, so it will go to negative infinity. Here we are. Now for -1, from the right, it goes to -infinity. It's doing something like this. And when it is going to 1 from the -1 from the left, it goes to infinity. So it will do something like this. Okay. Now we say that we have a horizontal asymptote. So it will at infinity, when it goes to infinity, it will approach 0. So it will have something like this. So initially we have the following graph. I think it is much better. Mine is better in this time. So here we are. So the graph is doing something like this. So I think, by the way, just we need to make sure, is it here concave up? If it is concave up, it will do something like this. Here, also here. If it concaves down, it should cross here. So I think it should do something like this, unless it has another مثلا local absolute maximum and value. It might do something like, no, it should pass through the origin. So let's say that it's doing something like this, and then it goes up and then go down. I need to know, but there is no x-intercept. I think خلاص, it will not intersect x again, so it should go back. So initially you can think about the graph, but you will not be sure 100% about it. So to make sure about how it looks like, you need to continue. Let's see what we can figure out more. So we have now, we need to know where it is increasing, where it is decreasing, where the maximum, the minimum, local maximum and minimum. So find the first derivative, ya shabab. This is the function. What is it? Here is the function. This is the function. Differentiate it by using the quotient rule and simplify. You need, ya shabab, to simplify. But it is not difficult to simplify here, because you will have here 4x cubed and here 4x cubed. They will be cancelled. And you left up with -4x over the square. After finding the derivative, what we need to find, ya shabab? What we need to find next?
Critical points.
The critical numbers, yes. So to find the critical numbers, in fact, if you can know where it is increasing, where it is decreasing without knowing the critical number, this will be good. Wow. But it is not easy, by the way. For this, it could be. For this function, it could be. But let's see. Now, what are the critical numbers? The critical numbers we have here when the derivative equals to 0. If this equals to 0, means the numerator is 0. When the numerator is 0, it means that x is 0. So this is one of the critical number. The another critical number is what?
Does it exist?
Does not exist.
Why? We have 1 and -1, shabab. It does not exist. It does not exist at 1 and -1. So are these critical numbers?
Yes.
No, because
Why?
not in the domain.
Yes, thank you. They are not in the domain. So be careful, ya shabab. This is why it is important to find the domain at the beginning. Let's go back to the domain. The critical numbers are not. The domain is all the real numbers except 1 and -1. So we have here only one critical number. One critical number only, which is x equals to 0. Okay, be sure, ya shabab, always the critical number is a number in the domain. So now what we will do this small trick. This is the only critical number that we have. It is okay to write -1 and 1 here, but they will not affect the sign. By the way, this is always positive. This is always positive. The denominator, because it is squared, it will be always positive. Don't worry about it. What you should worry about is this one. So now, if this is the derivative, we are talking about here the derivative. The derivative will be positive or negative after 0, ya shabab? Is it going to be here positive and here negative? No, because here it is negative. If we are talking about x, yes, it will be after 0, it will be positive. Before 0, it will be negative. But when we talk about negative x, it will be the opposite. It will be here negative and here positive. So what do we have? We have this. After 0, it will be negative because we have negative x, ya shabab, here. If you bought, for example, 1, this will be negative. If you bought -1, it will be positive. But we cannot bought 1 and -1 because they are not in the domain of the function, the original function. So what we conclude, ya shabab, from this? What is the conclusion? that we conclude that the function is increasing from negative infinity to 0 without negative 1, okay, and decreasing from 0 to infinity without 1, okay. So what is the maximum and the minimum? What will happen? What we have at 0?
Maximum.
Local maximum.
Maximum.
Local maximum, because the graph is going to infinity and negative infinity, ya shabab. So it will not be absolute, of course. And this is just a test for local maximum and minimum. Yes, you are right. So now I know that this point, it passes through the origin. This will be a local maximum. So it will do something like this. Okay. So I can now have an idea about my graph. Now also I know that it is increasing here from negative infinity to negative 1. It is increasing. And also from negative 1 to 0, from negative 1 to 0, it is also increasing. Log, it is increasing. But I need to make sure that it is concaving up, because of course it will, but we will see. It might concave up and then down, and we will see. So wait until the end, ya shabab. Now we have an idea about the local maxima, the increasing, decreasing from the first derivative. Any question?
Doctor,
Yes.
do you think that information or the guideline for drawing a sketch are more than what we need to draw a sketch?
For some functions, yes. Like this function, it is more than, yes, more than, yeah. Of course, sometimes you know how to sketch this graph, shabab, from 0, 0, 1. But of course, here we will be sure 100%. For this graph, for this function, I do agree with you. I told you I can sketch the graph without the derivatives. Stop here and sketch the graph. But of course, for other functions, it is not easy. You will see that. You will see that. When you are, ya shabab, sure, 100% sure about your graph, خلاص, sketch the graph. Now, what else? We said that the only critical number is 0. Now, if you want to know that when it is concave up and down, find the second derivative. It will take time because it is a rational function. So if you look at the second derivative, what we need to know what now, ya shabab? We need to know where it is positive, where it is negative. So if you look here, this is always what? Always positive. It will never ever be 0 even. So we need to just worry about this, where it will be negative if this is negative, okay? So in that case, it will be negative if x squared minus 1 is negative, and it will be positive if x squared minus 1 is positive. So this means that you need to consider the second derivative with negative 1 and 1 open, and remember that they are not, of course, in the domain. And of course, now it will be what? The second derivative. It is now x minus 1 times x plus 1. So it will be positive if, let me write the second derivative here. And here we have x minus 1, here x plus 1. So for x minus 1, it will be positive here, negative there. For x plus 1, it will be positive here, negative here. So in total, this will be positive here, negative, positive. Now here it will concave up, concave down. I'm talking about f now. F will concave up, not the second derivative. So now we know that it will concave up from negative infinity to negative 1 and from 1 to where? To infinity. Let me ask you an interesting question. Do we have inflection points? You know what are the inflection points, ya shabab, when it's changing from concave up to concave down? Is this inflection point? Is it inflection point?
No,
No,
Who
no.
said no?
No.
not continuous.
Who said no? Muhammad Sahli?
Yes,
Why, Muhammad?
not continuous.
What do you mean by not continuous?
It's a horizontal asymptote, a vertical asymptote.
They are not in the domain. Also, the
Yes.
inflection points are points in the domain. You are right, Muhammad. Thank you. Ya shabab, to avoid this, to avoid this mistake, always ask yourself, What is it? What is the inflection point? You know the point will be x and y. What is y? You cannot find it. Y, 1 and what? You cannot. Because the function, ya shabab, here is the function. The function is not defined at 1 and -1. So there is no inflection points here, ya shabab. Again, the same as we have done for critical numbers. The inflection points are points on the graph. On the graph. On the graph, points on the graph, at which, of course, the function is continuous, and of course, it concave change from concaving up to concaving down. I think I should, yes, I mentioned it here. I bought a row here and a row here to bring your kind attention to this. It has no inflection points because they are not in the domain. They should be in the domain. But it's still, of course, concaving up and down, as we said. If we summarize, ya shabab, all what we have gathered until now, look what we have. We have the following graph. This is our graph. Let me just clear it up. As expected, by the way, from the beginning. But you need, ya shabab, always check what you have done. Is it concaving up here and there, down here, increasing, decreasing, maximum local mix, maximum local minimum? Check everything. Is it symmetric about the y-axis? Because you know from the beginning that it is even. Yes. Look here. This is the y-axis. It is symmetric. It is like you have a mirror. You have a mirror here, and this is just the reflection on that one. Okay, I think, ya shabab, it is enough to. This is another rational function, but now it is not polynomial over a polynomial. It is a polynomial over a radical. So the idea is almost the same. Let me, ya shabab, skip this example. We will go back if we have time for that. So what you need to do, just you need to follow the guidelines. You need to start with the domain. The domain here is not closed interval or all the real numbers. It is just what is inside should be positive. So it is from -1 to infinity. I'll go back to this, inshallah, at the end of the class. But of course, there are interesting ideas that you need to know about such graphs. Also, this one, look, we have exponential functions here. I want to go to the. This is also about rational function that contains a fractional function that contains trigonometric functions. Don't think that it will be similar to the usual graphs, unless, of course, it is. Here, for this example, it is kind of periodic function. Logarithmic, how to do that with logarithmic functions also. Here we are, log. I'd like, in fact, why I run quickly over those examples, because if we don't have time to study them, it's okay, because you have everything here. The details are here. You can just follow the instructions. Let's now come to the main part of this section, shabab, the slant asymptotes. You have an idea about them from MATH101 and 002. For example, if you remember, shabab, the hyperbola. When you have a hyperbola, there will be two asymptotes, two slant asymptotes like this. So what is the slant asymptote? The slant asymptote for any curve, it is a line that when x goes to infinity, you have a graph. But when x goes to infinity, it will behave like a line. So there will be a line. The distance, the vertical distance between them is very small when x goes to infinity. So like this. So the distance, the difference between the function and the line, you know, this is the equation of a line. Usually we write it in terms of slopes and y-intercept. The distance between them, or the difference between them, is 0. So they are almost the same. They approach, they can be very close for each other when x goes to infinity or negative infinity, of course. So if we have a line like that, we call it slant. Why we call it slant? Because it is not horizontal, not vertical. If it is not vertical, or if it is vertical or horizontal, it is not slant. Slant or oblique, it means that is not horizontal and not vertical. It has a positive or negative slope. Now, this is important, and this is, I think, what is new for you. You didn't apply this idea, shabab, in MATH101 or 002. To find the slant asymptote, you need to check this. For example, if you said, oh, I know that 2x plus 3 is a slant asymptote for function, any function, let's say f of x. If you said that, you need to check if you subtract this line from the function and you take the limit when x goes to infinity or negative infinity, it must be 0. So this is the easier way to explain that. So the similar argument can be, of course, said when x goes to negative infinity. Is there anyone, ya shabab, remember from Math 001, I think, how to find the slant asymptote for rational functions? If you have a rational function, can we find the slant asymptote in that case?
When we don't have a horizontal asymptote.
We could, by the way, some functions they have, and of course also you have slant. Yes, you are right. It is when the degree, if the function is rational, when you have a polynomial over a polynomial, the slant asymptotes occur when the degree of the numerator, is 1 more than the degree of the denominator. So what does that mean? For example, if this is of degree 3, this will be of degree 2. So the numerator is 1 degree more. So in that case, you know that the limit of this goes to infinity. It will not be, there will be no horizontal asymptotes when x goes to infinity, but they could be when x goes to negative infinity. But they will not be in the same direction, of course. They will not be both to the right or both to the left. Now, usually how to do that? If you have a polynomial with degree 1 more than the degree of the denominator, what to do to find the horizontal asymptote? We will just apply what, ya shabab? The long division. Let's apply it for this example. Sketch the graph of this function. So we will do the same. It is rational, ya shabab. It is rational. You can know from the beginning that this one will have a slant asymptote. Why? Because the degree of the numerator is 1 more than the degree of the denominator. Now let's focus on the slant. How to find the slant asymptote, ya shabab? We will apply the long division. Let's apply the long division over x squared plus 1. You need to multiply by x, so it will be x cubed plus x. Subtract, it will be negative x. So how to write the result, ya shabab? X cubed over x squared plus 1 equals to what? The quotient plus the remainder over the divisor. So this can be written like this. Now, where is the slant asymptote, ya shabab? Here it is. It is a line of degree 1. So this one, which is y equals to x, is a slant asymptote. How to make sure that it is really a slant asymptote? Just take x cubed, which is the function, subtract the line. If the limit when x goes to infinity or negative infinity is 0, then it is really a slant asymptote. What we will do, we will just take the limit. Let's say when x goes to negative infinity. Let's take it when x goes to infinity. So what is my function? My function, it is x cubed over x squared plus 1 minus, what is my slant asymptote? X. So now what will be this limit, ya shabab, if you simplify? It will be limit x goes to infinity for what? It will be x cubed minus x cubed plus minus x. Am I right? Over x squared plus 1. I just wrote it as a single fraction. This will be cancelled. And what do we have here? We have here negative x over x squared plus 1. What will be, ya shabab, the limit?
0.
0, because the degree here is less than. If you divide by x squared, you will get 0. So it is. What will happen if it is going to negative infinity? The same. So even if it is going from the right or from the left, it will be the same. If this function, of course, are allowed to go to negative infinity. I think you know now how to find the slant asymptote. And we will see how to sketch the graph of the function when you have a slant asymptote by solving this example. So remember, ya shabab, the guidelines. You need to start with the domain. The domain of this is all the real numbers. Why? We have a denominator here, but the denominator cannot be never ever 0 for any real number. So the domain is all the real numbers. Now the x-intercept and the y-intercept. When x is 0, y is 0. So this is the y-intercept, by the way. Now when y is 0, x, when this, it will be 0 also. So this is why both of them are 0. Now the function is odd. Why the function is odd? If you replace x by negative x, you will have negative f of x. So it is odd. So it will be symmetric about the origin. This is good. What else? It is never 0, so there is no vertical asymptotes. No vertical asymptotes, ya shabab. Why? Because the denominator cannot be never ever 0, because the domain is all the real numbers, so it is continuous everywhere. And now you need to know about the end behavior. What will happen when x goes to infinity or negative infinity? What will happen, ya shabab? If x goes to infinity, this is positive. Don't worry about that. This is positive. When x goes to infinity, this will go to infinity. The degree here is greater than, so it will go to infinity. And when it is going to negative infinity, it will go to negative infinity because of x cubed. Because this will be negative if x goes to negative infinity. Negative infinity over positive infinity, it will be negative infinity in that case. So there is no horizontal asymptotes because it doesn't go to specific number. But I know now, ya shabab, that when x goes to infinity, the graph will goes up. And when x goes to negative infinity, it will goes down. And it is symmetric about the y-axis, about the origin. So it will behave, it looks like it will behave like x cubed. But of course, with the slant asymptote, we did find the slant asymptote. What is it? What was the slant asymptote, shabab? Y equals x. هذا هو السلانت asymptote. So we just write it when we sketch slant asymptotes, we will draw it like dot lines like this. So this means that it will they will approach each other when x goes to infinity. We have done that. We showed that y equals x is a slant asymptote. And you need to find, of course, the first derivative to know where it is increasing, where it is decreasing. This is the first derivative. You can see that this is positive, shabab. This is positive. And also this is positive. So what? It cannot be never ever negative. So it is always positive for all x. So it is always what?
Increasing.
Increasing over negative infinity to infinity over the whole domain. So what does that mean? There is no local maximum, no local minimum. Of course, it is always increasing. طبعا except at 0. Why he said except at 0? At 0 it will be 0 exactly. So we have a critical number, huh? We have a critical number at 0, but it doesn't change from increasing to decreasing at 0. It will behave like x cubed. The derivative is 0 there, but there is no local minimum, local maximum or minimum there because it is always increasing. We will have a local minimum or local maximum when it's changed from increasing to decreasing. Now, if you want to know about the concavity, the second derivative, this is the second derivative. Of course, it could be, by the way, here. It could be negative here, negative here. So you need to work here to know where it is. You need to do what? To find the zeros. Let's start with, this is the second derivative. The first, we have 0.
1 minus 1.
Square root, negative square root of 3. Square root of 3. And here, no 0, no problem here. Here it is always positive. This is always positive, shabab. Why it is always positive? Because this is always positive. When you cube it, it will be positive. So we need to just check these numbers. And remember that the domain is all the real numbers here. It is good. So now, remember that here you have 3 minus, let me write it in as a difference of squares. So we have here 2x square root of 3 minus x times square root of 3 plus x. Now, for x, it will be always, for this x, it will be after that positive, before it negative. For square root of 3 plus x, it is also After -3, it will be positive, 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 and here negative. Now for -3, you have to be careful because here you have x is negative. So after negative, after square root of 3, it will be negative. Before that, it is positive. Be careful, because x here, I'm talking about square root of 3 minus x. Now combine these, shabab. Here we will have positive, negative, positive, negative. Forget about these. Just you can use them as a check. Now this is the second derivative. What about the function itself? Here it will concave what? Up, concave down, concave up, concave down.
Down.
So this is inflection point, negative square root, and what? You need to find y. This is inflection, and this is also inflection. For sure they are in the domain. This is inflection. So you need to find them what they are, shabab. The table is there, but I think mine is better, shabab. Use this better, but of course, if you prefer to use this one, it's okay. So we have 3 inflection points. Here they are. This is x and this is y, x and y, x and y. And this will be the graph as expected. This is the horizontal, the slant asymptote log. When x goes to infinity or negative infinity, they will be close from each other. But of course, it crosses here. The graph, this graph, it is crossing his slant asymptote. Of course, there is an intersection point between them. If you bought your graph, this is your graph, x cubed over x squared. If you bought it equals to 1 to x, you will get that the solution, the x-intercept is 0. If you bought them equals to each other, and it is clear. They will intersect each other at 0. Now we need ya shabab to, we still have time. Yes, we need to practice. These are some exercises. Yes.
When we find the inflection point, we substitute the x's in the first function, right?
Yes, it's x and f of x, of course. They are on the graph. Always, shabab, we substitute when you find the critical numbers and if you want to find the maximum and the minimum values, substitute by the critical numbers on the function, and also when you want to find the inflection points. I mentioned here, shabab, 5 exercises from your textbook for you to practice finding the slant asymptotes. And I'd like to, this is easy. You will do the long division, long division, long division, long division. You can do that as I did in this example, shabab. Let me focus on this. How to find the slant asymptote of this one. And also there is an exercise here. This is a recitation. It is 71. It is in the recitation. You will solve it, inshallah, with your recitation instructor. This is also interesting one. So now how to find, ya shabab, the slant asymptote of this one? This is the question. Think about it, shabab. Think about it. While you are thinking about this, let me show you the old exam questions. Look, the first question, the slant asymptote of this. Let's go to the second question. The slant asymptote. The curve has slant asymptote, vertical, horizontal, no what, and so on. The tangent to this curve is perpendicular to the slant asymptote. You need to find the slant asymptote. Equation of the oblique or the slant of this one. Long division. This is easy. This is long division also, easy. This is similar to the recitation question that I told you about. How to find the slant asymptote of this. The solution is here, by the way, but it is ugly and ugly, by the way. This is not my solution, Shabab, by the way. This is as it is. You may have questions like this, by the way, in the final. So look here, you need to sketch the graph. You need to sketch the graph, and you have 5 choices. So even we can ask you some issues like that. Let's go back. Let's go back to the exercise, the exercise that I told you about. Now, how to find the slant asymptote of this? Any idea, Shabab? Remember what we said about the slant asymptote. The limit of the function minus a line, it equals to 0 when x goes to infinity or negative infinity. You need to think about this one. What do you think? So to know what is this line, you need to check first how it behave. Now when x goes to infinity يا شباب, when x goes to infinity or negative infinity, let's focus on infinity. This will behave like that. Like what? طبعا أكيد هذا راح يكون 1 plus 1 over 2x. طبعا this will goes to infinity. أكيد طبعا. This will goes to infinity. Now I'm interested on this one. This will goes to where يا شباب? When x goes to infinity. It will goes to what?
0.
To 0. لا لا. So it means that this function, the whole function, will behave like this line. So at infinity, this curve will be similar. Let's say this notation similar to this one. So what does that mean? It means that this line is what? Slant asymptote. Y equals this. This is the line, ya shabab. So it is slant asymptote. To check that, now we just know that this will be the slant asymptote. Now we need to make sure that it satisfies this. So now what I need to know that this is nominated. يعني الآن هذا مرشح إنه يكون horizontal إنه يكون slant asymptote. How to check? Just find the limit when x goes to infinity for this function, for the function اللي هي 1 plus a half of x plus e to the power negative x. الآن المرشح اللي قلنا عليها شباب هو هذا مرشح إنه يكون إنه it is nominated to be a slant asymptote. So what we will do, we will just subtract it. It will be minus the line, minus this, it will be minus 1 minus a half of x. And if you check, this will be 0. And you have limit x goes to infinity for e to the power negative x, which is 0. So it is a slant asymptote. Okay. Let's I'll give you the idea here.
Doctor,
yes.
Can we consider the slant asymptote as a linearization?
As a linearization, you mean?
Yes.
No, the linearization, no. The linearization, ya shabab, it is near a point. Be careful. It is near the tangency point. So the linearization is valid here only, not when x goes to infinity and negative infinity. Be careful. It is near a specific point, near 1, near 2, near the tangency point. Now, when x goes to infinity, ya shabab, this goes to where? Do you remember tan inverse? This will go to where, ya shabab?
pi over 2.
Pi over 2.
So this will be the here it is. This will be a horizontal slant asymptote. It has 2 when x goes to infinity, when x goes to negative infinity. Okay. طبعا here we didn't check يا شباب at negative infinity because this at negative infinity will goes to where? To infinity. So it doesn't have in that case. It will not be a horizontal slant asymptote line. Let's look at this. This is not polynomial over polynomial. If it is polynomial over polynomial, we will divide easily. But ya shabab, if you have a polynomial, let's say x to the power 4, x to the power 3 plus 1 over x squared minus x minus 2. At infinity, when x goes to infinity, this function will behave like x to the power 4 over x to the power 2 like x squared. Why? Because this is what we call it the leading term. This is a leading term, this is a leading term. So they will behave like x squared. So this is a very important idea to know. So it will behave like that. And the graph will look like that. Here, you need just to focus on this term and on this term. They will lead, they will dominate the behavior of the function. So this one, ya shabab, it is asymptotic. It will be asymptotic to 2x to the power 3 over 2 over x to the power half, which is it going to be a line or not? If you subtract, it will be 2 to the power what? 3 over 2 minus a half, it is to the power 1. It is a line. So this will be, it is nominated to be slant asymptote. It is nominated. What you need to do, you need to check that the limit of this minus this when x goes to infinity or negative infinity, it is 0. And you can see that the slant asymptote of this graph is 2x. If we have time, we will resolve this exercise, inshallah, again in the next class. What I forgot, Shabab, to mention, please, in 1 minute, let me stop recording.